eigendecomposition A equals PDP inverse, and the singular value decomposition of A, which is U sigma B transpose, and review all of the core elements. The singular value decomposition always exists for any matrix, even ones that are not square. The eigendecomposition is only defined for square matrices and only exists if we can find a basis of eigenvectors for the n-dimensional space. The vectors in the eigendecomposition matrix P are not necessarily orthogonal. That is, the changing basis is not simply rotation and scaling. On the other hand, the vectors in the matrices U and V in the singular value decomposition are orthonormal. They do represent rotations. Both the eigendecomposition and the singular value decompositions are compositions of three linear mappings. One, a change of basis in the domain. Two, independent scaling of new basis vectors and mapping from domain to codomain. And three, change of basis in the codomain. The key difference between the eigendecomposition and the singular value decomposition is that in the singular value decomposition, domain and codomain can be vector spaces of different dimensions. In the singular value decomposition, the left and right singular vector matrices, U and V, are generally not inverses of each other. They perform basis changes in different vector spaces. In the eigendecomposition, the basis change matrices P and P inverse are inverses of each other. In the singular value decomposition, the entries in the diagonal matrix sigma are all real and non-negative, which is not generally true for the diagonal matrix in the eigendecomposition. The singular value decomposition and the eigendecomposition are closely related through their projections. The left singular vectors of A are eigenvectors of AA transpose. The right singular vectors of A are eigenvalues of A transpose A, and the non-zero singular values of A are the square roots of the non-zero eigenvalues of both AA transpose and A transpose A. For symmetric matrices A that are n by n, the eigenvalue decomposition and the singular value decomposition are one and the same, which follows from the spectral theorem. Let's add a little practical interpretation for our singular value decomposition. We'll do this by analyzing data on people in the preferred movies. So let's consider three viewers, Ali, Beatrix, and Chandra, rating four movies: Star Wars, Blade Runner, Amelie, and Delicatessen. The ratings are values between 0, the worst, and 5, the best, and encoded in this matrix of data. Here our matrix A is 4 by 3. Each row represents a movie, and each column a user. Thus, the column vectors of movie ratings, one for each user, Ali, Beatrix, and Chandra's preferences. Vectoring matrix A using a singular value decomposition offers this way to capture the relationships of how people rate movies, and especially if there is a structure linking which people like which movies. Applying a singular value decomposition to our data matrix makes a number of assumptions. One, all viewers rate movies consistently using the same linear mapping. Two, there are no errors or noise in ratings. And three, we interpret the left singular vectors UI as stereotypical movies and the right singular vectors VJ as stereotypical viewers. We then make the assumption that any viewer's specific movie preferences can be expressed as a linear combination of the VJ vectors. Similarly, any movie's likability can be expressed as a linear combination of the UI vectors. Therefore, a vector can be interpreted as a viewer in the space of stereotypical viewers and a vector in the codomain of the singular value decomposition correspondingly as a movie in the space of stereotypical movies. Let's take a look at the singular value decomposition of our movie user matrix. The first left singular vector U1 has large absolute values for the first two science fiction movies, and a large first singular value, the red shading. Thus, this group's a typical user with a specific set of movies. These movies are science fiction themed. Similarly, the first right singular B1 vector shows a large absolute value for Ali and Beatrix, who gave high ratings to science fiction movies. That's the green shading. This suggests that B1 reflects the notion of a science fiction lover. Similarly, U2 seems to capture the French art house film theme, and B2 indicates that Chandra likes these types of movies. A science fiction lover is a purist and only loves science fiction movies, so a science fiction lover B1 gives a rating of 0 for everything but science fiction themed. This logic is implied by the diagonal substructure of the singular value matrix sigma. A specific movie is therefore represented by how it decomposes linearly into its stereotypical movies. Likewise, a person will be represented by how they decompose into movie themes. Let's take a look at another example. Consider a situation with 6 users and 5 movies, broken up into science fiction movies and romantic comedies. We can see that our first 4 users prefer science fiction movies, while our last 2 prefer romantic comedies. When we decompose our matrix A into U, sigma, and V transpose, we get the following 3 additional matrices. We'll take a second and look at each one individually. Let's first take a look at the V matrix. You can see that the first and second rows of V transpose, or the first and second columns of V, find science fiction movies and romantic comedy movies. The first 3 movies are science fiction movies, and you can see that the vector V1 points in the direction of those movies. Similarly, the last 2 movies are romantic comedy movies, and vector V2 points in the direction of romantic comedy movies. In other words, when this matrix sees a science fiction movie, it maps the movie to the science fiction direction, and a romantic comedy movie to the romantic comedy direction. We should note here that we don't need to worry too much about the signs. We're looking at magnitude. The signs will change depending on how you actually plug this into a computer. Next, we'll look at the sigma matrix. So once we have our values from V transpose, those values are then multiplied by the importance factor found in matrix sigma. So the science fiction direction is multiplied by the science fiction importance factor, so the first singular value. Subsequently, the movies in the romantic comedy direction are multiplied by the romantic comedy importance factor. We can see that the science fiction importance is roughly twice as much as the romantic comedy importance. And that makes sense because in this data set, there are twice as many science fiction fans than there were romantic comedy fans. We can also see that the first 2 entries of the singular value matrix, sigma, are so much larger than any of the other entries. This makes sense as well, as in this data set, the only directions that really matter are science fiction and romantic comedies. The other directions that the singular value decomposition is detecting here are probably from random variations among the fans and the movies of each genre. And those random variations do not matter really to the overall structure of people's movie preferences. What matters is the two groups of fans of the two genres of movies and the size of the first two singular values tell us just how important those are. Next, let's move on to our matrix U. The U matrix receives the movies in the sci-fi and romantic comedy directions after they get amplified by their respective importance factors and send those movies to the science fiction and romantic comedy fans. The first column, U1, shows where the science fiction fans are. We know that the first four users are science fiction fans, and the column U1 really have large values in the first four entries. Again, we shouldn't worry too much about positive and negative signs. Similarly, the second column, U2, delivers romantic comedy movies to the romantic comedy fans. Now here's the summary. The movie ratings matrix maps movies to users, and the singular value decomposition on that matrix tells us how it does that. First, the matrix V figures out which ones are science fiction movies and which ones are romantic comedy movies. We can call V1 the science fiction movie vector and V2 romantic comedy vector. Then the sigma matrix multiplies the relative importance to each genre of movies. If we see the science fiction movies are the most important in this data set, so they have the largest singular value, sigma 1. The romantic comedy movies are the second most important, so they have the second singular value, sigma 2. Finally, the U matrix delivers each genre of movies multiplied by the respective importance factors to the fans of those genres. The users pointed by the U1 vector receive the science fiction movies, and the U2 users receive the romantic comedy movies. In our next video, we will go into the mathematics of dimension reduction. However, we want to carry this example through, but skim over the mathematics. In our example, we had two critical types of movies. We're going to reconstruct A using only the key features U1, U2, sigma 1, and sigma 2, and the vectors V1 and V2. In mathematics, this technique is called low-rank approximation. It captures the most important dimensions in a given matrix and recalculates the matrix with those dimensions only. The resulting matrix is of lower rank, but it still retains the most important information from the original matrix. By applying it to our movie ratings matrix, we can confirm that it really does keep the science fiction and romantic comedy structure. So we go ahead and we reconstruct our matrix. We'll call it E2. You can see the matrix in the upper left corner of the diagram. Let's begin by seeing how similar our reconstructed matrix A2 is to the original matrix. You can see that high values in our original matrix show up as relatively high values in our matrix A2, and similarly with low values as well. What happens now if we have a seventh user, and that seventh user hasn't filled out all of the movie ratings? We can see that this user clearly likes science fiction and less so romantic comedies. If we did a singular value decomposition on this matrix, we might be able to create projections for science fiction 2 and 3 and romantic comedy 2. The problem is we've got missing values. And so we can't do any mathematics in this matrix without having some sort of value in those three spots. Let's go ahead and use 3 as a placeholder in those 3 spots. We're going to perform a singular value decomposition and then reconstruct the matrix. So we go ahead and do that. We can see that our missing values are now filled in. And we can see as well that it's given 3.8, 3.6 to our 2 science fiction movies and 2.15 to our romantic comedy. But is this just because people like the first 4 movies better on average? Not at all. If we redo this example and we swap our original 7th person as having 1 in placeholder 1 and 5 in placeholder 4, we actually get opposite values. We see that science fiction 2 and 3 are both in the 2s, and romantic comedy number 2 is almost 4.